Good afternoon, everyone. Thank you for coming. I think we have very good attendance today. And how do you like the conference so far? Good? Enjoy it? Boring? Hopefully not boring, okay? Okay, cool. Thank you. Yeah, I think it's a good start of the afternoon. So today I'm going to talk about the paradigm shift. And I really want to focus the move to the distributed SQL. And I'm Liquan, and I'm currently a senior database engineer at PingCap. And prior to PingCap, I've been working at Pinterest Confluent, working on big data, especially in the streaming systems. Some maybe the most challenging problems in ads, which is calculating the spend for each ad to ensure that we are not overspend the customer's budget. This sounds like easy, but it's actually a very challenging problem. And in my spare time, I'm a big fan of open source, and I have been contributed to Apache Kafka and Apache Spark before. I do have a question for you guys. So actually, PingCap is my fourth job. How many years do you think I've been using MySQL in my previous jobs? 1 year, 2 years, 3 years, 5 years? Actually, 0 years. Okay, so in my previous 3 jobs, I have never using like MySQL or any relational databases. This may be an interesting fact to remember. I think this also correlates some of the topics today. So I want to start with some big pictures. That's a really good thing. So I think, in summary, today's world, and people start building applications using the cloud primitives. And they start using the services provided by the cloud provider or third-party vendors to build their applications. And as a result, there are many new applications are born in the past few years. For example, there's many SaaS IPOs, and there's many fintech vendors like Block, like the other, like internet banks. And there's also booming of digital native business like social network, search engines, and other stuff. And those new applications has new requirements. Here's a summary of them. I think the first requirement is that they need to support a high concurrent number of users, and potentially can be billions of users. And those systems need to be highly available. They need to be at least 4 nines these days for any companies comfortable using them. And the interaction with those applications should be low latency, and you see more and more data-driven insights and actions. I believe these days you are using DoorDash, and you do see DoorDash has automated result customer services. If you're missing some items for your order, and you click customer services, they will first offer you a free credit automatically without like talking to a customer service representatives. So I think those insights are already built into the application. Yeah, here are a few other examples. I think in SaaS, like Salesforce, you do see those user-facing dashboards, and there are many automated actions and alerts you can make from those applications. And they usually use ad hoc queries to find anomalies in your system. For example, finding the best performing reps or the worst performing reps in your company, things like that. And in fintech, there's a constant theme of reconciliation between different sources to make sure the balances matches the transaction history. And there are ongoing needs of the fraud detections. And in the digital native business, like social network, you do see those machine learning powered recommendations in your feed and in search results. So there are many new applications, and they have new requirements. Let's take a simple example. I think this is probably the dumbest or the simplest e-commerce platform you want to build in the world. And it only supports the current maybe 4 or 5 functionalities. First of all, we can make an order from a store on a certain product with the price you paid. And then you want to query the orders by the user, and you also want to query by the store. And as the operation side, you want to occasionally analyze the performance of the stores and find specific stores with low or high performance. There are a few characteristics of this e-commerce platform. First of all, this application is multidimensional in the sense that you don't need to query by different identities. For example, you want to query by the user, and you also want to query by the store. And when analyzing the performance, you need to run aggregations and selections. By aggregation, I mean you need to calculate the sales by the store, and you also want to find the top performing stores, or like low performing stores. I think when the scale is small, building this e-commerce platform is very easy. I think the traditional relational database offers all the necessary support for building this application. You have the beautiful secondary indexes allows you to query by different entities. That is the key to support the multidimensional nature of this application. And when the scale is small, you have the luxury to run the analytical queries on the same store as you run other transactions. And this is pretty easy, right? This is a happy parse. But many people want to have this happy problem, scalability. You actually want your application to be popular. You want users to grow to 1 million, even to 1 billion, maybe in a month, right? That's the happy problem people want to solve. But when you meet this happy problem, when the number of users increase, naturally the data volume increases because all the people are making transactions. They will generate the data. And then all the people start making requests to the database. And naturally the read and the write KPIs will increase. And then your used to be easier, the analytical queries now start to impacting your transactions and slow everything down. This is one dimension. Naturally, as user grows, you have this scalability problem. On the other hand side, I think your product managers may want to add more fancy functionalities to the database or to the application. For example, they want to add some intelligences. I think one intelligence for this store may be that we want some real-time inventory management. That means you need to have a real-time monitoring of all the stock for all the product. And this can also have the complex query on your system. Then you have your problem. This is a heavy problem to solve, but this is a pretty challenging problem to solve. And how do we solve this heavy problem? I think there are mainly 3 options. And the first one is shard your database. And the second option is to move to NoSQL. And the third option is to adopt a complex architecture. I believe this audience, I think you guys are experts of databases. So I'll just talking about the issues you may encounter with those different options. Here I have a question I want to ask. So how many of you has sharded a database before? Raise your hand, please. Do you like it? Okay, cool. And how many application code do you have to rewrite after sharding? So thousands of code, couple hundreds or couple thousands of code. And yeah, I think I believe that people don't like it from the reactions I see. I think there are a couple issues with sharding. So first of all, when you do sharding, you have to choose a partition key. And when you choose a partition key, there's no global secondary indexes because of the nature of that sharding business. Then when you have to query on the key that is not the partition key, you do need to rewrite your application in order to do that. And because sharding system is a collection of independent running MySQL or database instances, it's very hard to support complex queries like joins and things like that. This is the application development side. You have to change your code. And once you do that, you also lose a lot of nice properties provided by the database. And from the operations perspective, after shard, we need to add more machines. There's always a manual step involved, and that usually has a downtime. No matter how smart it is, there's usually a downtime. And the restarting process can typically take a couple of weeks because of that. And once you're sharding, there'll be no out-of-the-box transaction support. And their schema change won't be synced across different nodes. I think that those are challenges with sharding. Now let's take a look about what the issues with NoSQL. I think NoSQLs are good. I think they solve the scalability problem. But however, they provide much simpler semantics. They usually don't support IC transactions, and developers have to code with eventual consistency. Importantly, there are typically no flexible secondary indexes, and as a result, it's really hard to provide complex queries with NoSQL semantics. And oftentimes, the users or developers against NoSQL are actually solving the database problems, like the IC transaction problems. I think if you are, I was a user of NoSQL, I know the pains. I'm not sure whether you have been using NoSQL and share the same pain. Let me know. Okay, I want to quickly know that in this audience, who is currently using NoSQL, and are you happy about that? Which database, which NoSQL are you using?
Mongo and Dynamo.
Do you like them?
Yeah.
Okay. Okay.
Not pretty happy, but okay.
Okay. Cool. Yeah. Do you have to code against some the lack of some stronger semantics like transactions?
Yeah, it's a problem when you need a complex query for range.
Yeah.
Dynamo, we need to use an elastic search in the architecture to compensate.
Yeah. Yeah.
Problems.
Yeah.
It's a complex architecture.
Yeah. So I think with NoSQL, and if you want, yeah.
I use NDB cluster.
Okay.
Substantially, and it does handle the complex queries very well because it can distribute and join
Yeah.
nodes and collect them all.
Sure, that's nice. I think I'll talk about something similar to you in the later of the presentation. Okay, and the third option is that people, as this gentleman mentioned, they will adopt a complex architecture to handle the limitations of NoSQL. For example, using a NoSQL plus Elasticsearch to handle the search, and maybe another or lab database to handle sort of complex queries, right? And this is very typical architecture I see in my previous company, or also maybe other companies. They have online layer, and they have a offline layer, and they have a serving layer. But it solved the problem. It works, and those companies also make billions of dollars a year. But however, this architecture also has problems. I think the first problem with this architecture is that it's complex, as the name suggests. So people have to maintain multiple systems and maintain those ETL pipelines. I think in my previous company, there's a data team. The data team has more than 30 people, and they maintain those pipelines. I think I have two jokes, while working in those companies. I can share with you these two jokes. And the first two jokes is that, okay, I think the best time working for those companies is when you're newly joined, and you have the chance to write those pipelines. But after you write 3 or 5 pipelines, you don't have the luxury to write more pipelines. You have to make sure the 5 pipelines you wrote is running properly. Basically, they need to dedicate their whole time managing those 5 pipelines they wrote. I think the second joke is my personal experience. I'm working at ads. I think I call myself, I'm actually infra engineer, but I call myself as a ETL engineer because the majority of job is actually copying data from a system A to system B. For example, copying data from, let's say, Elasticsearch to our ad server, or copying data from database to Elasticsearch. That is a major job. And once you do that, I think writing those code is not the worst. Validating the data between the system is the same is the worst. Especially you are running streaming pipeline. It's really hard or even impossible to validate the data in different systems are actually the same. And if they are not same, you may lose money. So there are two codes. And I think the second issue with the complex architecture is that this incurs additional cost because different systems are built to be highly available, which means that they will have multiple replicas. And you do need those multiple replicas, not because your business needs them, it's because of limitations of each system, and you do need to make copies between different systems. Yeah, that's kind of a waste of money. And the third thing is also very painful, is delays and consistency issue. It's really hard or even impossible to make sure that there are strong consistencies between different systems. Yeah, I think the problems I just described is not alone. It's not just happening to this like maybe simple or naive like e-commerce platform. I think it's everywhere today. And I also had the observation that the complex tech stack is already used for those new applications. And many application developers actually need to solve the database problems on a daily basis, which is not very fun. Some people may like it, I like it, but it may not be that reliable when solving those problems. I think the second observation I have is that the ACID transactions really eases developers' life. I think these two code, I think the first code I have is actually from our TiDB users, and this is what he complains about building applications using NoSQL. I think I read about it. I think there are frustration and applications either to live with the eventual consistency or code around it. This is pretty time-consuming usually. And the second code is from the Spanner's paper. I think based on Google's like many years of operational experiences on building applications using NoSQL like Bigtable, they think it's still valuable to bear the cost of using stronger transactions versus always coding around that in the application. So based on those observations, what's on the wish list for a database? I think it's really important to have ACID transactions. I think this is beautiful. Once you have that, you can safely retry, right? It's really reduce the burden on the application developers to code with the partial failures. And you want scale. I think the scale is that you don't need to worry about database to be the application bottleneck once you have many users or once the complexity of the system is there. And we also want the expressiveness of SQL. Then you can really express your business logic in the SQL instead of like express logic in the application code. So that is kind of the motivation. I think with this side, I want to switch gear a little bit to talk about TiDB. Okay, sure. I hope you buy in the story. Actually, you don't need to listen the second half. You can maybe hear another two presentations in the second half. I think the first half is really what is more important. This is what I wish to have when I work at my previous companies. I think if we have a distributed SQL, no more sharding, that is highly available and strongly consistent, a lot of problems can be very easy to solve. And the developer velocity can be faster. So TiDB is a database like that. It is not a fork. It is not a middleware. It's not a SQL on Hadoop. It is a distributed SQL written from scratch. And it can use MySQL client to connect to it. And this is a very high-level overview of its architecture. And it has 3 major components. The TiDB servers are the computation layer. And on the right-hand side, there's a TiFlash or TiKV servers. Those are storage servers, are storing data in the row format or column format. And we also have Python driver that serve as the brain of the system, collecting the metadata and making sure the data in the system is balanced. And it also handles a failover in the system. I want to talk a little bit about how the data is represented, or how the table is represented in the TiDB. So I think this, as illustrated in this graph, so TiDB is a layered architecture, and the TiKV offers a transactional key value database. And the tables and the indexes in TiDB are actually represented as key value pairs in TiKV. And they are sorted by the dictionary order of the key. So this may be a little bit abstract, but the key here is that both the data and the secondary indexes are represented as key value pairs. Okay, so here a row in the table is represented as a T with the table ID and the row ID, and the value are the columns. And then the index is represented by a T and the index ID with an index value, and that point to the row ID. Here's an example. For this simple user table, we have index on the name, and the name is also represented as key value pairs for the indexes. Same with the table data. And physically, this is a logical representation. You can think about TiKV as a giant key value map. But physically, those giant map is partitioned by the key, and we call each segment as a region. And each region has a size of 96 megabytes. And this is like unit of data movement. You can think about this region either contains the table data for certain ranges or the index data for certain ranges. And these regions are highly available, and we are using the Raft protocol to make sure that they are consistent. Okay? So let me recap a little bit. So the tables are represented as key value pairs in TiKV. Okay? Also, same with the index. Index are also represented as key value pairs in the TiKV. And there's no difference between table and index in the storage format. They are all key value pairs. Go ahead.
So like region 1 in this example, is that a complete copy of the data, or is it split between node 1, 2, and 3?
Sure, great question. So let me talk a little bit. So you have giant table, for example, here, right? Your giant table here, a giant table here, and the key are ordered by the dictionary order, and we basically split the big table into smaller chunks, and each chunk is called a region. And the region is 96 megabytes. It can be the case that many small tables are in the same region. It can also be the case that a table spans multiple regions. Does this make sense? Okay.
So in that example, one table might be region 1, 2, and
Yeah, one table and maybe 1, 2, 3. You see that, right? In this case, the table data is actually scattered and distributed across different machines.
So in this example, region 1 and region 1 and region 1, those are the same copies of the
Same copy, the same data, and the raft protocol is used to make sure data is consistent between those, among those copies. Okay, so that's really important. Also, in this picture, I want you to know that not only the data or the table data is distributed, but also the index data is also distributed. Okay, I think this is the foundation of the distributed processing capability TiDB offers. And I think one thing here, this is how the transaction is supported in TiDB, because this is very involved. It cannot be covered, I mean, in maybe 20 minutes. But the idea is that once you have the replication protocol, the changes to multiple regions will be handled by a transaction protocol. It's a basically decentralized two-phase commit protocol to ensure modifications on the data in different regions satisfy the ACID properties. Okay. So this is maybe a recap of what I just mentioned. So basically, inside TiDB, we use logs.db to actually store the data. Okay. And then in the logs.db, we have the many different regions, right? And in the regions, it can either store the table data or index data. Okay. Any questions on this? Okay, cool. And I also want those regions can move, because these are the unit of data movement. Once you add a new node, let's say you have TiDB5 here, and because when you add that, there's no data, and the PD, which I mentioned in the architecture slides, is called placement driver. That will actually move some of the data from those 4 TiDB nodes to the newly added nodes automatically. This is actually goes through a raft process. You need to first add a new replica in the new node, and then remove the old replica from the old node, or from the node that hosts this data originally. It's actually a copy and then remove, a delete. Yeah. Okay. So because the table and the indexes in TiDB are distributed in different nodes, and naturally, when we do query processing, we can do parallel query processing, right? So think about the TiDB nodes. They receive a SQL query. It will parse it, optimize it, and then it also serves as a route to execute this query. For example, if you want to write select star from a table, or let's say select count star from the table, and these operations can actually push down to the different TiDB nodes, because this aggregation can be parallelly processed by different TiDB nodes. And this is the magic that makes TiDB can handle more complex queries like aggregations much faster compared with single node MySQL. And this is another example here. This is join, and this is query plan. You first need to do some table scan, then do filtering, and then we need to join. And this we can actually push down this filtering to the TiDB node, because we don't have to need to put the data back to all the way to the TiDB to do this computation. Okay, so that is parallel execution. And this is also very cool. This is called HTAP feature in TiDB, and HTAP is short for hybrid transactional and analytical processing. What does it mean? It's actually a very interesting question. It means that TiDB actually has column stores and row stores. And the column store and the row store are in sync during the read time, or during the write time. And during query processing, it can determine which data to read from, which copy, where to read data from, depending on the query. Here's an example here. So if the query is on a table scan, then it's probably faster on the column store, and then the query will be executed in the column store. If the query is a point get or a index lookup, it will go through the row store. So TiDB offers a smart selection in the query optimizer to determine to read from to execute the query from both row store and column store. Yes. Yes, the query optimizer is cost-based. Okay, I think one way to interpret this is that because the column store and row store are strongly consistent, you can treat the column store as a index. And you can also build a cost model around that. And definitely, query optimizer can search from a larger space by reading from this index and choose even a more optimal plan, considering without this, right? So, yeah. Okay, here's a very high level of some features provided by TiDB. And the next section, I'll talk about from a different angle. I want to talk about from the application developer's angle. Why should you use TiDB to build new applications? I think the first one is that TiDB offers strong consistency. It supports full IC transaction, and developers won't need to handle the data consistency issues in the application, and the users won't be impacted by the anomalies caused by eventual consistency. Yeah, I think the way we do it is through multi-version concurrency control with timestamp ordering and two-phase commit. I know this is a pretty fun talk. I think you can follow us maybe in our meetups. I think we will provide some in-depth introduction to how our transaction works in our meetups. But if you're curious now, and there's a paper we published in YugabyteDB 2 years ago, and there's a whole section on this, on how the transaction works in TiDB. And TiDB is so highly available. By that I mean the operations on TiDB is mostly has no impact on the application. For example, no rolling upgrade, scale out, scale in, has no impact on the application. And the schema change also is non-blocking, is online. And TiDB has also built-in mechanism to handle failures. So in general, TiDB is highly available. And the third thing, and in TiDB is real-time, is timeliness. The couple aspects of this. The first one is that the data in TiDB is fresh. Once the data is committed, it is available for querying immediately. And we also offer secondary indexes and push down and parallel query processing to ensure that the query latency can be slow. So with data freshness and low latency queries, you get the timeliness. And the last thing is the scalability. TiDB is horizontally scalable, and you can add more nodes to store more data, process more reads and writes, and handle more complex queries. I think these features make TiDB very easy to handle user growth or add more product functionalities. If you want to build applications with TiDB, and here's reference architecture, and I think TiDB, because of it has strongly consistent transactions, strongly consistent columns and row stores, and highly available, you can actually use it for a lot of workloads. For example, the traditional RTP workloads and the workloads by the new application, for example, like SaaS. And in SaaS, you always have some sort of a dashboard, ad hoc queries, and TiDB can be good for that as well. And then you can also use TiDB to be a system to satisfy your user-facing or external-facing applications, as well as internal operations, such as monitoring the KPIs and of different stores and figure out which things are going wrong. So there are a couple of different patterns that can use TiDB. And as a summary, TiDB brings simplicity back to the application developers. I think you can, from the application perspective, we can basically use TiDB as a single node database. It's like database. You have the secondary indexes. You have the column store and row store, you got SQL. But the underlying is scalable, it's highly available, it handles the failures automatically. So it meets the requirements for the new applications. And it will handle the HTAP workload because of the column store and row store. Yeah, then you can use it to power the internal analytical applications. So yeah, that is the talk. Then I will spend maybe another 5 to 10 minutes on a quick demo so that you see what TiDB is about, okay? So before I do that, any questions? Okay, cool. So,
Does the column store compress?
see then, does column store compress? I think so, it's compressed, right? Yeah. Yeah, okay. Yeah, basically what we did, let me maybe spend 1 minute on that. So ClickHouse is good for aggregations especially, and they have a lot of specialized code to run aggregations for different cases. But ClickHouse is not good for their query optimization and real-time updates, right? So this is maybe the challenge for all the column-based or ORAP databases. And we add another layer, we called it a dirt merge tree, to basically process those updates and ensure that the transaction order is maintained in the dirt spaces. Yeah. Yeah. Okay. So can you see that? This is the sketch of the demo. So this is a very basic demo, and I believe there may be more cool demos for tomorrow's talk by our co-founder and CTO, Ed Huang. So today's demo, I just want to make sure the couple of basic stuff. First of all, we have a tool called TiDB that allows you to install TiDB very easily. It usually can do that with a single configuration file and a few commands. And here I'm going to use the demo tool called Playground. Basically, you can spin up a local cluster very easily using just one command. And then I will show you how can you use MySQL client to connect to TiDB, which demonstrates TiDB actually very compatible with MySQL. And then I will show that, I may skip this. The ID index in TiDB is non-blocking, which means that you can still run the DMLs, run the queries when you're adding indexes. And the fourth thing I want to show is that after you insert data to TiDB, you can immediately query it. So there's no delay. And you can view the query plan, you can view the metrics, and then scale out and scale in the TiDB server, TiDB servers very easily. So then let's start. Can you see that clearly? Is that better? Okay, so let's see. One more, okay? Is that okay? Let's do this. Is that okay? I don't know. Probably okay. So, yeah. Cool. So TiDB Playground. So basically download a few packages from the online repo, and then it will start different services. And typically this is done within a couple, maybe 30 seconds. Now it's working, right? And then you can basically use a MySQL client to connect to it. Let's go from there. Yeah, you see that? And then you can run select version. This is this is TiDB version. This is not MySQL, right? I'm not like TiDB version, yeah. And then the second thing I want to show is that TiDB actually offers a few very interesting tools. And the first one is a TiDB dashboard. And typically, this is our. It has information about the clusters and the queries and slow queries and all those statements running on the system. I think, for example, you can see the slow queries here. Also, you can see your cluster topology. You can see the host, disk, and statistics. And you can also search logs in this system. You can select all instances and search for maybe TiDB, and you can return for it, right? You can also search maybe on certain instances, and also search for that, yeah. And we also offer a key visualizer, which shows the key access pattern on the TiDB to figure out whether there's hotspot or not, because TiDB is range partitioned. There can potentially be hotspots, but we have ways to mitigate that. And by reading this graph, we can actually figure out which key ranges or which table indexes are hotspots. And we do have a demo on our booth, and you can show more interesting patterns. Yeah, this is one tool I want to show. And the second tool is really the graph and the metrics. And you can see we have the mean and check, close, and skip. And then in that, we have basically the operational metrics for different components of TiDB. For example, you can see this is the TiDB like metrics, TiDB servers, and these are the like, yeah, they can also see the TiDB servers, which are the storage servers. TiDB details, discard. And this is what happens in the TiDB. And you can see there can be like the raft processes, and as well as the push down like coprocessor details. And you can usually use this to debug issues in TiDB. And then I want to mention that TiDB support different deployment methods, and this is a deployment on using containers. And TiDB can also be deployed on Kubernetes. And we have a TiDB operator that allows to deploy TiDB on Kubernetes and manages using the Kubernetes controllers. What else I want to talk about? Okay, and then I think, yeah, let's make some table maybe. So let's do this. So we can create a table here and insert some dummy data. Insert some create table and insert some dummy data. Okay, let's sleep for a few seconds. Then we can see that this is only one region available and start with table ID 65. It's a bit boring because it's only a few data points. But once you insert more data, you can see this region will be split. Because initially you only have a small amount of data, there will only be one region. And when you insert more and more data, because each region wants to be kept as 96 megabytes, and then the region will be split.
How do you handle the data rebalancing for hotspots?
Yes, cool. I think there are a couple of things to do. So we do have some like QPS-based scheduler and load-based split. So we can gather the load on a certain region and on a certain machine. There are two ways to handle it. It can be the case that multiple hot regions on a single machine, and then we'll split them out to different nodes. It can also be the case that a certain key range is very hot. It has many read and writes. And in that case, we handle that by splitting the region to smaller pieces and move that around. So that's a strategy to handle. This is automatic process. So we have the PD can collect those information and then send a command, and TiDB will execute those commands to move the data around. Is that locking balancing occurs? Nope. Okay, cool. Okay, so I will also do another demo. So what that?
Not even on the metadata? No locking even on the metadata for that?
So basically, the metadata is stored in. This is an interesting question. You mentioned that during the split, whether we have locking on metadata. I think the answer is no. And the reason we handle the split is through the Raft protocol, because this deals with the bigger regions split to smaller regions, right? And this is really consensus on the metadata on how the region start and the region end. And we basically have a split command and execute that through the Raft machine to ensure that different replicas are on the same state. Yeah. And then let's do add index. I'm not sure this, but let me connect to it using another shell. Okay, so let's do this. Let's do outer table and add index here. Okay, so we see that it takes some time. And what I want to show is that you can still insert this data to it, but my hand may be too slow. It may already finish. But I mean, use the test. Okay. But the good thing is that we can do it again. So we can alter table as it's running. We can still insert, it's working, and it's still running, right? There's non-blocking DML on a DDL. And if my hand is fast enough, you can still probably see using this command it's still running, but then it's probably not. Then let's do it again. And you can see there's an ongoing DDL running. It's running in the background. And the way to work is that it actually take a staged approach. If you're considering ID index, there are several stages. It can first be available for delete only, right? Basically, when you delete some data, you need to delete this index, otherwise you corrupt your database. And then it becomes the write only, which means that when you insert data, you need to update the index, otherwise you also corrupt the database because you have data and index inconsistency. And then after these two stages, you will basically backfill the data from your table to the index. And once backfill is done, then you can make this data available to query. So that is a staged approach to add indexes. And because of this, during this process is non-blocking because we can control when the index is available for serving. So you don't have to block. Yeah.
And I guess while the index is being backfilled, you would probably just default to like a full table scan, probably, right?
Yeah, you are not going to use this index. You probably use other indexes available. Yeah. And I think that we have 1 minute left, and then that concludes my talk. So let me know any questions. We can do offline discussion, stay our booth, and maybe come back again tomorrow for our co-founders talk and Jeff's talk. Yeah. Okay, cool.